So hello everyone, this is lecture 35 for the quantum mechanics. So today we will start a new topic, that is harmonic oscillator, in which we will study that how at the quantum level we will have the discrete energy levels. But classically we see that energy can be continuous. But here we will see that energy will be in this form, means discretely divided, where the we know that in the black body radiations we have studied, the Planck gave this expression, means the energy will be in this form like nh nu. But before studying this, we will see the questions I have given you in the last lecture. So they were about the finite potential well and the infinite potential well. So in this one, this first question was a particle of mass m is confined in 1D potential well, and potential was given for different ranges. And we need to find the eigenfunction and the bound state, number of bound state. Then we need to plot the phi x and the phi x square. So it's just the same as we did in the finite potential well. There it was plus v naught here, and it was 0. So it's just a simple difference, means here it will, if you add plus v naught in all these three, it will be v naught, 0 and v naught. So that will be finite potential well again. So you will get the same expressions, because let me show you what kind of equations you will get here. So here you will just use a time independent Schrodinger equation, and it will be E minus V, and energy will always remain mod of E, that is negative. So E minus V will give you, and V is negative again, so it will be V naught minus E. So here you will get these kind of equations. Then you can assume K2 square, and this is for the R2 reason, and for the R1 reason, you know, this V is 0, so it will be 0 here, and E is mod minus mod E, so it will be minus. So R1 will give you this, and R2 will give you this, and R3 will give you this. Now you have these equations are the same as we studied in the finite potential well, so you will get the same solution. So just the difference is only the minus V naught. So this is the same case, just a reference is difference. Now, and again plot will be also same. So let's see the next question. A particle of mass m is confined to a finite 1D potential, and Vx is given V naught, and that is mod x greater than or equal to L by 2, and 0 mod x is less than L by 2. So it is again finite potential well. So they ask us in its ground state the wave function satisfies the condition. So phi x is a at x equal to 0, and phi x is root 3 by 2a at x equal to L by 4. And we need to find the value of wave function at x equal to L by 2. So let's put the boundary conditions. So we know what are the solution for the finite potential well. So these are the solution, means for the ground state it will be even, then it will be odd, even, odd, even. That's how you get. So for the ground state, the phi x will be in this way. So let's substitute the conditions given. At x equal to 0, it is given that phi x is equal to a. So phi x equal to a at x equal to 0. So at x equal to 0 means between this range. So it will give you c, and again phi 1x must be equal to phi 2x at the boundary. So at x equal to 0 it will be a. So a will be equal to c. So from here, just c equal to a, this will cancel out. So cos k2 L by 4 equal to root 3 by 2, and k2 L by 4 is nothing but pi by 6, that is 30 degree. Now from here you can find the value of k2, that is 2 pi by 3L. Now substitute the k2 here and c equal to a, then you can just means at x equal to they asked they find the value of wave function at x equal to L by 2. So L by 2 will lie here. So at x equal to L by 2 it will be c equal to a. So just substitute the values. So in place of c we will have a, and in place of k2 substitute this value, so you will get this. So it will be again L will cancel out, 2 will cancel out, pi by 3 will give you 1 upon 2. So a this phi x will be a by 2. So this is your answer. Next they asked us that find the ground state energy of the particle. So again, to find the energy of the particle, you know that it is given k2 equal to root 2 me by h cut square, and k2 we already find it. Just substitute this value here, and this will be square of this, and from here energy will be this. So this is the required answer. Now next question is, consider a system whose wave function at t equal to 0 is this. So wave function is given, and phi x is the wave function of the nth accelerated state of infinite square potential well, where say. So En is given, and we need to find the expression value of energy. So first we need to find the probability, only then we can find the expression value, because if we E1, E2, E4 we know that E1 will be from here, E2 will be 2 square, E4 will be 4 square. But how to find the probability? So it is some kind of C1 phi 1, C2 phi 2, C3 C4 phi 4. So probability for phi 1 is nothing but C1 square divided by C1 square, C2 square, C4 square. So C1 square, C2 square, C4 square, if you add them they will give you 1. So the probability of first one is simply 9 by 30 is for 16 by 30, and this is 1 upon 6. So just substitute the value of probability and energy, you will get the answer. And we know expression value of energy always remains same after any time or the evolution of the wave function, it will remain same. So, and the time dependent wave function you can find just directly from here. So here h with the first eigenstate will give you h1 e1, and h with the second eigenstate will give you e2, and for fourth it will give you e4. So that's how you will get your time dependent so matlab wave function. Next question is a particle of mass m in infinite value of length a has the following initial wave function at t equal to 0. So initial wave function is given, and we need to find the energy, what values will you find, and with what probability. So for that, we know that this is the first eigenstate, and this is second, and this is third. So energy values you already know eigenvalues, but how to find the probability? So for that you need to find the C1, C2, C3. So here the under root 2 by a with this will make the wave eigenstate, and with under root 2 and C1 you have to find that C1. So you know how to find that. We already did this kind of question. So let me show you again. So here this 2 by root 7a must be equal to c1 under root 2 by a. So from here you can find the value of c1. Again, this term should be equal to c2 under root 2 by a. So there you can find c2 and c3. So you will get these values c1, c2, c3, and the square of them will give you 1, means it is a normalized wave function. And probability of first one is simply square of c1 square, that is 2 by 7. For second it is 3 by 7, and for third is 2 by 7. And energy eigenvalues will be this. Now exponential value of E is simply E1, PE1, PE2, PE2, and E3, PE3. Now to find we need to find a time dependent wave function. So it is simply psi xt is nothing but exponential minus ist h cut, and this is the time independent wave function. So this is the time dependent wave function. You know how to find this. So this is the time dependent wave function. So next is determine the probability of finding the particle at a time t in the state. So we need to find the probability. So this is simply just phi, and phi star you need to find. So the inner product of phi and phi star will give you probability. So it is exponential minus iota, and phi star will give you plus iota here, and dot product and the integration will give you, this will be 1, and this will give you 1 upon a sine square 3 pi x by a. So you just need to solve this integration, and that will give you 1 upon 2. That will be your answer. Now next question is, in this itself, calculate the probability density rho xt and the probability current density jxt. Verify that this is the equation of continuity, so we need to verify that also. So the probability current density is nothing but it is a probability, means flow of probability inside a potential, that per unit area per unit time, that is called the probability density, current density. And probability density is simply psi star psi. So let me show you this. So probability density is simply psi star psi, and you know this is psi is time dependent one. So we already find the time dependent wave function. So we'll just take the conjugate and do the dot product. So here we see that all the eigenstates are orthogonal to each other. So psi 1 means the phi 1 of psi star will give means only product with the phi 1 of psi. So we'll get only 3 terms, and that will give you square of this, and this will give you the probability density, that will be 1. Now del rho by del t is 0, means because rho is some constant, that's why it will give you 0. Now to find the probability current density, this is your formula. So we already discussed the probability current density, so there you derive this formula. So this is the formula for probability current density, I h cut by 2m psi del by del x psi star minus del star psi star del by del x psi. So you already know psi, so just to calculate for first one, and for others you will get the same result. So this is your psi xt. Now just do this for this first one, means put this one in this. So find the psi star, will give you plus iota, and psi you already know. So take the differentiation of psi star and substitute in this equation. So this is, let's I just solve this for first one. So del by del x of psi star will give you this, and psi dot del psi star by del x will give you this. Then I did for the second part, means this one, and this gave me this. So this is the same, just like this. So subtraction of this minus this will give you 0. So this j is again 0. So they satisfy this equation, means others will give you the same results. So that's how you can verify. This is the equation of continuity which all wave functions satisfied. Now next question is, consider particle and infinite square well whose wave function is this. So wave function is given ax a square minus x square x 0 to a. So this is the infinite square well potential. So that's why it will be 0 otherwise. So we need to find this a so that psi x is normalized. So you need to find the a. So how to normalize the wave function? It is simply psi star, and the integration dx should be equal to 1 between 0 to a. So you can do this like, wait. So we'll normalize it like this way. Psi star psi dx equal to 1, and now just substitute the value of psi star and psi. So from here you can just find the value of a, capital A, that will be equal to this. So just put this factor and this wave function will be normalized. And now we need to calculate the del x del p and uncertainty in the position momentum. Then we need to find the del x del p. So you already know the formula of del x. We already solved this one. So for del x, we need to find the exponential value of x square and exponential value of x and square. So this will give you del x. So for that, you need to find this del x. So del x is simply formula is this x inside, and for x square it will be x square inside, and you need to solve this again. That will give you these values, and just substitute here, you will get del x. And again for the del p means for del p you need these two values. So it is again minus I h cut del by del x. We already solved this kind of problem in the last. So you can do this and substitute here del x del p, then you can find the product. Now for the third one, calculate the probability of finding this for a measurement of energy. So we know here n is equal to 5, so it is a fifth state. So probability means it is a fourth excited state after the ground one is considered as 0. So probability current density JXT means you must know this definition also. Probability current density is JXT is nothing but flow probability per unit area per unit time. So we were here. So we need to find the probability of finding this. So let's see what is the probability. For probability, you must know the coefficient of this fifth state, that is C5. So for that, we already know that phi 5 and psi will give you C5. So the inner product of phi 5 and psi will give you C5, and the square of C5 will give you the probability of fifth state. Because this is a normalized wave function, that's why C1 square, C2 square, C3 square all will give you 1. That's why the square of simply C5 square will give you the probability of fifth. So this is how you can find this. So this is a simple integration you can solve, just a little bit lengthy, but it can be solved easily. So that will give you the probability of fifth excited state, sorry, fourth excited state and the fifth state. So now, well, there is one more question remaining. I left it, I don't know how. So here, consider a particle of mass m confined in this. The particle is found to be in a bound state with energy E equal to pi square square 32 ml square, and we need to find the V naught. So this is a case of finite potential well. So we already stated in the finite potential well these transcendent equations. This K1 equal to K2 tan K2 L here is nothing but A by 2, and it is also A by 2 in that case we studied. So this is given. So energy is given. So we can find the K2. How we can find the K2 with energy? So the formula is K2 under root 2me by h cut square. Just substitute the value of E which is given. So this product will give you K2 equal to pi by 4L. So just substitute here K2 equal to pi by 4L. This will give you pi by 4 again, and here also pi by 4. So these both will give you 1 1. So K1 can be K2 or K1 can be minus K2. So K1 can be plus minus K2. So in place of K2 just write pi by 4L. So now we know this equation alpha square plus beta square equal to R square. So alpha is nothing but K1L and beta is K2L. So square this and just substitute here equal to R square. We know what is R. R square is 2m V naught L square by h cut square. From here you can just this L square will cancel out and substitute the value of K1 K2, that will be same, square will same, pi square 16 L square. From here you will get V naught equal to pi square z square divided by 16 ml square. So now as questions are done, so let's move to the topic. Next topic, that is harmonic oscillator. So I told you that in the quantum level we have discrete energy levels, that is in the form of this. So in the 1900 the Planck's already given this expression, and from his observations, and see today in the 1926 we seen that this is the same as expression given by the Planck. So at the quantum level we have this kind of energy. Okay, so we need to prove this expression now. So to prove this expression, we know in the quantum mechanics what we do. First we write the Hamiltonian, so then we find the eigenstates and the eigenvalues, then we write the time independent wave function, then we write the time dependent wave function. So that's how we proceed. So for the harmonic oscillator we know that there will be potential energy, that will be this. So and this force is nothing but gradient of potential energy. So and force in the harmonic oscillator we know it is some kind of minus kx. For this means it is always restoring force in the negative direction of the displacement. So this is your potential energy. So for this kind of curve we need to write the Hamiltonian. So it will be means this is for the classical mechanics, but in the quantum mechanics we know h is nothing but p square by 2m plus half m omega square x cap square. So this is your Hamiltonian. Now see, if we proceed the way I told you, so that will be it must be 20 pages long procedure. Means we need to solve the Hermite polynomial and all. But Now there is a way, means they find a way, means they just introduced a new operator here, that is a. It can be anything, it's just arbitrary we have taken, and we defined it with some prefactors, and that helped us to solve this equation or the Hamiltonian in very easy way. So how can we do that? So they just assume this in terms of the position and the momentum operator. So this is the prefactor for position, this is for momentum. So this, they assume this a. Now a dagger will be simply plus will become minus, and we call this as lowering operator and we call this as raising operator. So I will tell you in the detail that how we call it as raising or why we are calling it as lowering. So just for now, just assume that they introduced this operator and they used it to solve this Hamiltonian in an easy way. So from here it's kind of means it's a two variable equation in terms of the x and p. So you can find the value of x and p in terms of a and a dagger. So x and p will be this. So simply is a two variable equation, you can solve this. So x and p will be in this way, and a is not a Hermitian operator, means a dagger is not equal to a. So now you have x and p, and if you find the commutator of a and a dagger, that will be 1. And you know what is the commutator? We studied in detail the commutator algebra, that is ab equal to ab minus ba. So you can see that lecture again for the revision of that thing. So this will give you 1. Now they introduce a new operator n, that is a dagger a will be called as n cap, not cap, it's the n operator, and n operator is a Hermitian operator, n dagger equal to n. So just for now you just need to remember that we introduce a operator, that is this, and we taken the a dagger, and we again introduce a new operator, that is n, which is a dagger a, and a is not a Hermitian operator and n is a Hermitian operator. And if you find the sum commutator we will need in the derivation, that will be na is nothing but minus a. If you try to find this commutator, it will give you minus a, and na dagger will give you a dagger, and a dagger will give you 1. We already seen this. Now they also call the a dagger is called a ladder operator. So when we study that they are raising and lowering, then we can understand that how we are calling it ladder operator. So let's see them. Now we are assuming that lambda is the eigenstates of n with eigenvalues lambda. Means for this n operator, we are having the eigenstates in terms of lambda. So eigenvalues will be in terms of lambda. So n operator with the eigenstate will give you a eigenvalue lambda. So normally we just introduce eigenvalue in terms of the eigenstates to make it easy. It's just for the writing purpose. So n lambda equal to lambda lambda. So this lambda is the eigenvalue and this is the eigenstate. Now if you operate some new that this a operator on the lambda, then it will give you again some eigenstates. So that will be some different eigenstate, that will be zeta we can introduce. So we need to find this new zeta, we can say. So let's see how can we find them. So there is a simple procedure, you must remember this procedure. So operate n on a lambda. So this n will go inside and it will be na lambda. So we know what is na. So we remember na is minus a. This is the commutator of na. So it is na minus an equal to minus a. From here you can find the an, that will be equal to na. It will be na equal to minus a plus an, that will be this. So substitute here in place of na, we will substitute an minus a, and we will just distribute it inside. So it will be an lambda minus a lambda. So from here this n lambda will give us lambda lambda from here, and now this will be minus a lambda, and this is lambda a lambda a lambda. Now see, from here we can just take this a lambda eigenstate common, it will give us lambda minus 1 a lambda. So see, we operate this n a lambda and it will give us lambda minus 1 a lambda. So see, this is the same eigenstate we described as zeta here. So this is this. Now what you can observe from here, it is just like when we operate a on the eigenstate, then it will just reduce eigenvalue by 1. So we can just introduce, means that's how we define this a as the lowering operator. So a is a lowering the eigenvalue by 1 unit, that's why it is a lowering operator. So now hope it is clear to you why we are calling it as lowering operator. Now similarly, if you in place of a, you will just proceed with a dagger. In the last you will get lambda plus 1, that's why it is called the raising operator. The a dagger will give you this lambda plus 1 a lambda. Now see, this is a new eigenstate, and we can just means as we introduce here for the writing purpose, that with the lambda eigenvalue you should write lambda here, So same for the lambda minus 1 eigenvalue, you must write lambda minus 1 eigenstate here. So this is nothing but equal to lambda minus 1, and this is nothing but equal to lambda plus 1. So we introduce this. This is simply, this must be equal to this. So it is just a new eigenstate. So now to find the C value, how can you find a C value? So for that, just take this first one and take the dagger of this first equation. So this is a simple procedure you can remember. Take the dagger. Now this will give you cat will turn to the bra and it will be a dagger, and this is nothing but, this is again C star, and it will be lambda minus 1 bra. So now this is the equation, and just product this equation and this equation. So this will give you lambda a dagger a lambda, and C negative is square, it will become a square, and this. So this is nothing but 1, and this a dagger a we already defined, this is an operator, and this is this. Now this is what? This n lambda will give you lambda lambda, so lambda will be taken out, and the product of lambda lambda will give you 1. So it is lambda lambda lambda, and this will be 1. So from here C is nothing but, C negative is nothing but under root lambda. So you have find the C lambda, C negative. Now to find this C positive value, we again take the dagger of this whole equation, and we'll proceed with the same procedure. It will give you, means it will be like this, a dagger lambda, and after taking the dagger, it will give you lambda a, and C positive lambda plus 1. Take the product of these two equations. So again it will be a dagger, and here it will be, this will be 1. A dagger is nothing but n plus 1. So how it is n plus 1? We know a dagger is 1, so it is again commutator of a dagger minus a dagger a equal to 1. From here a dagger equal to 1 plus a dagger, and this is 1 n. So it will be n plus 1. Now there n lambda gave us lambda lambda. Now n plus 1 lambda will give us lambda plus 1 lambda. So it will be C plus, from here it will be under root n lambda plus 1. So our C positive is this, and C negative is this. So C negative is under root lambda. So we have find it this values. Now we have to find the energy. So for that, what is the main purpose? Main purpose is to find that energy values, discrete energy values, these ones. So for that we need to write the Hamiltonian. So now how can we write the Hamiltonian? So we already defined x as this and p as this. So n is simply a dagger a. So if you write the Hamiltonian, this was your Hamiltonian. Now substitute these values and use this. So you will get h as nothing but h cut omega n cap n operator plus half. So this is a very simplest expression now we have as compared to this. If we solve with this expression, then it will be a very long process. But with this equation, it will be a very simple process. So eigenvalues of h, let's means now see, if you just commutate the h and n, you will get 0, means h and n are commutator. So what is the meaning of that? Means they will have the same, means they will share the same set of eigenstates. So if lambda is the eigenstate of n, then h is also have the eigenstate as lambda. So lambda will be eigenstates of h also. So that is the meaning of commuting. Now n lambda gives us lambda lambda. So h is also gives us, means h is the energy operator, so that will give us eigenvalue as energy eigenvalues. So it will be h lambda is e lambda. Now h operator is nothing but, we reduced it into this form, so it will be this lambda e lambda. Now it will give us, in place of n lambda, it will give us lambda. So n plus half will give us lambda plus half. So this is nothing but energy eigenvalue. So energy eigenvalue is nothing but h cut omega lambda plus half. Now this the value of lambda will give us different eigenvalues of energy, means with the different eigenstate we will get different eigenvalues. Now there are proofs that lambda will always be greater than equal to 0. So we can see that also, means there are some constants on lambda. So this is the expression you already got. Now we need to find the values of lambda also. So lambda will be will always be greater than equal to 0. So we can prove this also. And lambda is lambda lambda. So take the lambda this side, and it will be, means one more lambda this side. So this will give you this kind of expression. Now this is giving us the lambda. Now if you say this, it is nothing but a dagger a. So this is our phi and this is our psi, and this is nothing but probability. So this will give you the square of this, and this is always greater than equal to 0, and that's why this whole thing is equal to lambda. So if this is greater than 0, then lambda must be greater than equal to 0. So that's how you can prove that lambda will be always greater than equal to 0. And also lambda will take only integer values. So there will be also this proof of this. So I will give you in the next lecture the proof. But for now, you must remember that lambda will take only the integer values. So in place of lambda plus half, we can just write n plus half, and n will be going from 0 to infinity. So it will be n plus half. Now energy eigenvalues will be, put n equal to 0, it will give you half h cut omega. For 1 it will give you 3 by 2 h cut omega and 5 by 2 h cut omega. So that's how you will get the energy eigenvalues. So in place of lambda we can write just nn as nn. So where n is the integers. So we'll see in the next lecture how it is only integers. So that's it for today. Thank you everyone.